Hello and welcome to your Experiment 2 pre-practical lecture. Right, so in Experiment 2 you're going to look at the decomposition of a nickel complex. And very important, you must remember that a decomposition is a chemical reaction. There's one reactant in the nickel complex or whatever is decomposing. However, there is going to be several decomposition products, especially when you're looking at a complex. The specific complex which you're going to look at is a nickel complex that is tri-coordinated to a bidentate nitrogen ligand, phenanthroline, and phenanthroline looks something like that. This is the lazy way or the more or less cumbersome way of drawing the nickel complex, and this is it drawn out. You can see it's quite intense. This is what we expect of you to draw if you refer to it in your report. However, it's also fine to draw it like this, since this is not CMY 385. Okay, like I said, this experiment will consider the decomposition and hence the rate of decomposition. So, meaning we're looking at reaction rates, like in CMY 282. And also, I think in 285, you completed one experiment looking at this. Okay, so you looked at a similar reaction in CMY 285, and there you had a trans isomer which isomerized to a cis isomer. However, in this situation, we're going to have, and that way you could look at that situation as a decomposition of a trans isomer to a cis isomer. However, here we're looking at a different kind of decomposition. So it's the same idea, just different kind of reaction. However, you need to look or to come up with what are the decomposition products. Well, we're going to talk about what the decomposition products are, but for now, you should have an idea of what decomposition products are going to be. And of course, you can use the literature, so the Basalo et al. Article, as well as the practical guide to help you to predict those decomposition products for this experiment specifically. Of course, you should also review your 282 notes on reaction kinetics if there is anything that you are uncertain about regarding this specific reaction. Because I am involved with this course as well, so I'm quite sure you do cover reaction kinetics in your second year. Okay, now the most important difference between CMY 285's experiment you did last year and this year's experiment is that with the 285 experiment, you weren't able to discriminate using a specific wavelength or absorbance at a specific wavelength. So in this case, we can discriminate between our complex, where it specifically absorbs at 420 nanometers, versus all the decomposition products, which they feel is like a million of them, but all of them, of course, decompose at, absorb at their own wavelength, which is likely not 420 nanometers. Just for interest's sake, you can see here, so the first decomposition, so decoordination, basically is what we're looking at, right? And you lose one ligand, lose another ligand, then you're just left with nickel, and of course, there's a protonated version of this. So this should start giving you an idea of why it decomposes, because what is the driving force between what's going on here in terms of the ligand and what the ligand looks like here. Okay. But what you need to take from this slide is our complex will only absorb at 420 nanometers, right? Then the kinetics at 420 nanometers. Then I say some mathematics, meaning the practical manual, you can read that on your own, gets to at some stage to an expression of ln A is equal to ln of some expression, there's an L and an epsilon and a concentration of some species, minus K1T. And of course, we all went to grade 2, so we know that y equals a minus bx, which is the same form as here, is a straight line. Only now that y is ln A is our intercept, which is the ln of something, and then b is our rate constant. And of course, x is t, but you know, you can swap things. But by plotting this, you're going to get a straight line, and you can do that using Excel, which we taught you in week 1 just to help you out a bit. And you're going to do this for 2 temperatures and use the Arrhenius equation, which we're going to go through now because this slide wasn't very informative. Okay, so in terms of the experiment, how you start. Firstly, you're going to synthesize the complex, which is much easier than we did in 385. This is basically a shake and bake. You're going to dissolve your nickel chloride, hexahydrate in water. You're going to add the ligand and you're going to shake, which agitation means basically it just means shakes. We will form the ligand, which has a charge of 2+, which needs to be neutralized by 2 chlorine ligands. So if it were to crystallize, your chlorine would have been your counter ion, and this would have been your salt. So it would have formed a salt, in essence, which is your crystals. But luckily, we're not going to crystallize anything here. We'll work in solution. So you need not concern yourself about this. Okay, so to drive the decomposition, we'll be using a strong acid and a lot of excess acid. So we'll only use 5 milliliter of our wine red solution, so Y of our complex, and we'll use 50 milliliter of a very strong acidic HCl solution, and we'll add our complex to this 50 milliliter HCl solution, and of course the acid will do exactly like you expect. The acid will decompose our ligand or our complex by protonating the ligand and causing it to decoordinate or discoordinate, whatever you like to call it, essentially destroying the complex. Right. Of course, you can also read Barsalo et al. On this. They do an extended version of it with different concentrations, different volumes, different all sorts of things. So just you can read that and see what they get, the rates that they get. They do a very nice experiment on it. You do a smaller version of what they do. Just a note on it, please do use the pipette pump that we provide you with. So either the normal pear bulb or the actual pump bulb, as I indicate here. Never suck on a pipette because, of course, you work with HCl as well as all sorts of germs are around, and there's like a whole pandemic. Hopefully, you're not watching the same video in 2075. Or hopefully I'm not presenting this course in 2075 still. Anyway, yes. So anyway, that's the point of the slide. Okay, so now that you have your 2 55 milliliters solutions made up, so your acid and your complex, you place them in the 2 different temperature water baths. Of course, you record the specific temperatures at which they are because they won't be specifically at 35 or 45 degrees Celsius. And then you're going to take measurements or absorption measurements at time 0, 5, 10, 15, up until 30 minutes. You take every 5 minutes, and then thereafter you only take in half an hour increments up until a full 300 minutes have passed. I know 5 hours seems like an age, and it will feel like an age. That's why I say please read a book. Then you will need to run a blank and zero the instrument on the first run. So there are 2 instruments that we can use. One is a instrument that is provided in the lab, in Joel's lab. If you use that instrument, you will only need to run the blank once at the beginning of the experiment. And you blank or zero the instrument once, and then it's zeroed for the rest of the experiment, and you don't need to run it again. If you have to use the UV-vis instrument in the instrument lab, then you will have to continuously run a blank sample. So there is a difference between when using a blank on just the first run versus continuously. So you need to make a note of that depending on which UV instrument you'll be using on the day. You'll probably be using the one that is in Joel's lab. So you'll probably just blank on the first run, but in case you need to use the one in the instrument room, then you'll be blanking concurrently or continuously throughout the day, throughout your 16 measurements. Okay, as I say, please bring a rather book. There's no computers allowed in the lab. You won't be allowed to go to the lecture halls because you need to monitor your Erlenmeyer flask with the little weights in the water baths over the period of decomposition. Okay, so once you have all your absorbance measurements and you have your time intervals when you took them, so you took different time intervals, so at 0, 5 minutes, 10 minutes, etc. You took different absorbance, you're going to make a plot of ln of that absorbance versus time, and that should give you a straight line. From that, you can determine a line of best fit using Excel. If it doesn't give you a straight line, then just make it a straight line. Okay. Of course, you just take whatever the fit is, whatever the correlation is, you just plot it as a straight line. If something went wrong, something went wrong. Of course, you have two lines of best fit, one at 35 degrees Celsius, one at 45 degrees Celsius, and of course, these are one at 33 and 46, or whatever your specific day is. Please don't use just 35 and 45. And then, of course, from that, you get two different rate constants. Because remember, rate constants are temperature dependent. So in other words, a rate constant will have a specific, will be correlated with a specific temperature. So K1 at the lower temperature and K2 at the high temperature. Some other things that you need to keep in mind. Remember, the temperature needs to be in Kelvin units. And also remember, if you use your time in minutes, and you keep it in minutes, you can also use it in seconds or whatever you would like to use it. That will just influence whatever your your rate constants units are then. Okay. So once you have K1, K2, your two temperatures, then you can use the Arrhenius equation. So equation 2.10 in the practical guide to calculate the activation energy for this specific reaction. So in other words, the specific conditions that we have the reaction in. So the 50 milliliters of 5 molar, so you know that specific reaction that we've had, that activation energy we can calculate. An important I just mentioned here, remember there's a gas constant there. That's why you need to take note of the specific units you use. So whatever units you want to use, if you want to use potato hectares per football field, you're more than welcome to work in that. But you just need to remember that at the end of the day, your R units need to cancel with whatever temperature and time units you used to use in your K units. Okay, right. So that's that slide. So essentially, we measured A versus time, then you plot ln A versus time, you get a straight line. From the slope, you get K. K is specific units, and then you plug it into this equation and you calculate EA. Easy as that. That's all you have to do in this prac. And then just a final note on the discussion questions. I know they might seem a bit difficult, but they really aren't. But you can use your time while your flasks are on the water bath to ask questions to your demonstrator. You're more than welcome to ask myself any questions you have. And they actually just ask exactly what they ask. There's no hidden agendas. There's nothing to catch you out. Specifically question 2, which asks you, how would you go about determining if it were second order kinetics responsible for the decomposition? Remember, this is a first order kinetics decomposition, which I take you can read the practical manual on. But how would you go about that? And it's really as simple as going back to your 282 notes and looking at what was asked there, because I'm quite sure there was a question at some stage that said, determine what order or what's the rate order of the following reaction. And then you had some sort of test for 0th, 1st, 2nd, or higher order reactions. And that is exactly what we're asking you to explain here, for example. So do some research, use your time wisely in the bath, and yes, then I will see you in the lab. Good luck.